All right, hello everyone. Welcome back to Historical Geology 1404. We are continuing in Module 1. We are discussing, we are having our review of rocks and minerals today. So, still mostly the same stuff that you're familiar with, but I'm just going to review the things that you need to be reminded about the most to understand what comes later in this course. Before we do that, though, any thoughts, any questions? Anything interesting you want to talk about? China just announced a brand new 1 million ton deposit of rare earth metals. The rare earth metals. So these 17 over here that you see on this chart, yes, extremely rare. You really only find them dispersed with other metals and such. And so whenever you find ore or rock that is rich in those particular kinds of metals, rich meaning, if I went outside and I picked up a rock, it might have 1 part per trillion of lanthanum, right? Or lanthanum. Okay, but an ore would have 1 part per million of lanthanum, right? So significantly more, but still very little. But the fact that there is more in there makes it valuable, right? So they've got the potential to produce 1 million tons of rare earth metals with this new deposit. Means a couple of things. I told you in 1403, China already owns the vast majority of the world market on rare earth metals. Remember I told you that? Like 98% of all rare earth metals are produced from China right now. Which means they've really got, to put it bluntly, they've got the rest of the world by the short and curlies, right? Because all they have to do is turn off the production or the dispersal of rare earth metals to whoever they don't like, and then that country cannot produce complex technology. You need it for microchips, you need it for all sorts of computers, you need it for anything that really has processing capability. Everything from missiles to Xboxes to your smartphone has rare earth metals in it. It's a big part of why those things are expensive, is how rare these metals are. So they found a lot more, which means that it's that much more control they have over the market and the rest of the world. The United States has several places that would work very well for rare earth metal mining so that we could be a competitor. But perhaps you'll recall I told you this last semester. Every time the United States, or a company in the United States, I should say, tries to start one of these mines, China drops the prices on rare earth metals just a little bit. Not enough that everyone's like, oh yay, but enough that any potential competitor gets run out of business. Because the only way that you can compete in this environment is if you can charge high enough to make up the cost of what you invested. It takes about $5 billion to set up a rare earth metal mine. And so if someone is investing that money and then the price drops and it looks like they won't get a return on that investment, they have no choice but to drop the project. That's happened a few times. China, think what you will about China, but they are extraordinarily savvy business people. They are ruthless business people. Not only with us, but with their own. That's a big part of the reason why they can make so much money off of it effectively, is because of their worker policies. I'm sure it's no secret that you get paid basically nothing compared to American wages in China. And they don't feel bad about it. The government doesn't feel bad about it because of the way their government is set up. And they've got the people to the population to use, basically. That's what it comes down to. Anyways, that aside, very interesting implications for the mining industry, the geology industry, and world economies there. No one noticed anything in the news? The Department of Education. Yeah, ain't that a thing? Okay, so the Department of Education has been hollowed out, let's say. Yeah, gutted. What form it will come back in, I'm not sure, but it's interesting. Actually, a number of agencies were shut down. The Department of Education just being one of them. My dad works at the CDC. I think I've mentioned that to y'all before. He works in the CDC headquarters based out of Spokane for the Northwestern states. Half of his division was let go last week, and all of the mining safety division was let go, and half of his projects were canceled. He's lucky enough to still have a job, but I was talking to him, and he's telling me, based on how many people have just been let go and the jobs that they had, he fully expects there to be large-scale industrial accidents starting again within a decade because no one's overseeing the safety of these industries anymore. It's interesting where we're going. Yeah.
Another thing happened to NOAA.
Yeah. I didn't hear anything specific about NOAA, but I would not be surprised if they got pretty well shattered up as well. I know that 3 different departments at NASA were just completely shut down, including, unfortunately for me, the one about policy, which is what I'm doing my dissertation in. I was never, at least as of right now, I was not planning on working for NASA. But even if I was going to, then I can't anymore because their policy division was shut down. It's far more likely I would have landed somewhere in the private sector anyway, but oh well. Good morning. How you doing? Great. You have a good weekend? I love your Cars backpack, by the way. Yeah. Do you like Cars that much? Or is it just a convenient backpack? Oh, okay, cool. Love it. All right. Sebastian, would you grab the door for me, please? Thank you. Well, let's go ahead and jump in. Last time we did a brief overview of Earth as a system. As part of that review, we talked about the rock cycle. Well, we're going to focus in on the components of the rock cycle, mostly having to do with sedimentary rocks. Not going to lie, because a huge component of this course is fossils and the environments those fossils come from and that we can interpret by studying those fossils. And that all is purely sedimentary rock. Okay? So here is a rock cycle. Now you saw the rock cycle before in this. This is a nice, literally circular demonstration of the rock cycle. But this is one that is not nearly as linear, I suppose you could say. It doesn't go in a nice, neat loop like that. But it does show where the different components can tie into each other. And it gives you different examples of each one of those different components. So you can find this on a slideshow for today's lecture. This may be a very helpful reference for you in future days. Just bear that in mind. So, starting from our magma, making our igneous rock, we classify our igneous rocks with certain characteristics, certain properties, and then from there into metamorphic rocks and sedimentary rocks, and there's a few things happen in between like metamorphosis and weathering and erosion and diagenesis, lithification, all that jazz. Okay, so that's what we're going to review a little bit today. Starting off with our discussion on matter. What is matter? Nothing. What's the matter with you? Tough crowd. Okay. All right. Matter. It's the stuff that makes things. Stuff. Stuff is a tricky word, isn't it? What do I mean by stuff? Well, in the American language, stuff can mean, like everything. Name one word in another language. I'm actually curious. I don't know if there is another word like this. Name another word in another language where you can say something like stuff, stuff, and stuff. And each one of those different, like I said, 4 words right there. 3 of them were stuff, and each one of those words stuff meant something totally different from the rest, right? It's weird. It's a weird thing. But anyways, that tangent aside, matter. Matter is atoms, okay? And atoms are made from 3 particles. Can you remind me of those particles? Electrons, neutrons, protons. Okay, there they are, protons, neutrons, and electrons. The protons and the neutrons together make a nucleus, and the electrons make that electron shell, or multiple electron shells, depending on your atom, right? So, electrons have a net negative charge. Protons have a net positive charge. Neutrons have neutral. They have no charge, okay? Your protons and your neutrons and the nucleus together make what we call the atomic mass, or the majority of the atomic mass. Technically, the mass of the electrons are still in there, but it's so minimal that we don't really talk about it that much, okay? Your electrons, the number of electrons, dictate, bless you, the electric charge in that atom, okay? Now, atoms are often drawn toward each other because of opposite electric charges. If I have an excess of electrons in my atom, it has a negative charge. If I am lacking electrons in my atom, it has a positive charge. Just like how the 2 poles of a magnet are drawn to each other. You know how magnets are drawn to each other? Why is that? It's because one of them has a negative pole and one of them has a positive pole. Have you ever had 2 magnets that you push together and they'll click, but then you turn one of them around and it repels? That's because all of a sudden you're trying to push 2 positive or 2 negative poles towards each other. Okay? Whereas a positive and negative are drawn toward each other. That's the nature of magnets. Kind of the same principle here. Okay? Positive and negatively charged atoms will be drawn towards each other. These electrons do not make nice, continuous orbits around the nucleus, like a planet would around the sun. Okay? Instead, they make this sort of haphazard shell. Okay? They travel in what I refer to as an electron cloud. Less of an electron orbit, more of an electron cloud, which makes a solid barrier. Why is it solid? That could just be one electron making that barrier, and it would still feel solid. That's what gives things resistance. The electron shells in my fingers are interacting with the electron shells in this table. Okay? These things are traveling extremely quickly. I don't remember, 5,000 plus miles a second. Okay? Something like that. I think it was I don't remember the exact number, but it's very, very fast. Now, the octet rule, also known as the rule of 8, states that an atom will gain, share, or transfer electrons until it has 8 electrons in its outermost shell, the valence shell. Okay? That's the outermost electron shell. Why it does that? That's an excellent question. It's a rule of nature, apparently. Couldn't tell you why. It just is. But 8 seems to be the magic number, which is why we have 8 columns here, excluding these metals down here. Okay? 8 columns here on our periodic table. They are divided into those columns because of the number of valence electrons they have, going from 1 valence electron to 8. These ones in row 8 or column 8, we call those noble gases. They are stable. They are not seeking to bond anything. We call them inert gases because they do not seek to bond anything. Typically, we can force them to by doing a few things, but typically on their own, they are inert, aka unbonding, okay? Not bonding. When 2 atoms are drawn towards each other, you can have a variety of different bonds that form from that. Ionic, covalent, and metallic bonds. Perhaps you'll remember those. In this example right here, this is an ionic bond. So we have sodium, which has 1 valence electron, chlorine, which has 7. Guess what? They want to be joined together so that they can, as a unit, have 8 valence electrons, and they do. So the sodium gives its electron to the chlorine, which means that it now has a net positive charge. Why? Because it lost an electron. It's no longer balanced. Our chlorine now has a net negative charge. Why? Because it gained an electron, which means that it has a net negative balance. And that positive and negative charge keep these two things bonded to each other. Okay? Here is an example. Carbon. Where is carbon on our periodic table of elements? Which column? Did I hear you say what? 6? Oh, it's number 6, right? Its atomic number is 6, but which column is it in? 4, which means it has how many valence electrons? 4. Good. Okay, so here we have a whole bunch of carbons. Here's one up here. Look at this. 1, 2, 3, 4 valence electrons. Perfect. Now, when carbons approach each other, when they bond to each other, how many does each one want? 8. So it needs 4 more. And so the ideal arrangement for carbon is actually to be bonded with 4 other carbons. Let's look at this one. 1, 2, 3, 4. Each one of those 4 donating 1 to this, now this one has 8 valence electrons. Satisfied, perfect, loves it, great. And each one of these is bonded to 4 carbons. 4 carbons around each one of those carbons. Everyone is satisfied. This perfect framework of all these carbons bonding together into this tightly woven pattern, this crystalline framework, this is what makes diamonds. And this is why diamonds are so difficult to break, why they're so hard, is because of this tightly woven pure carbon framework, where every carbon is satisfied electrically. It makes a very tight crystal, okay? Very tightly bound, dense crystal. And that's what makes diamonds, the hardest naturally occurring substance we know of. Okay. Atoms change in a couple of different ways. If I were to add or remove a proton from my atom, it would change the atomic number, right? Carbon, for example, is 6, meaning it has 6 protons in the nucleus. If I add a proton, what does it become? What? What's the next one? What's after 6? Huh? No. What's the next one? If I add 1 to 6, nitrogen, thank you. Okay, it becomes a nitrogen. You add another proton to a carbon, and it becomes, all of a sudden, it's a nitrogen. Okay? That's how the mass number works. What if I remove electrons? We just discussed what happens there. What happens when I remove electrons? I change the charge, thank you. Change the proton, change the mass. Change the electron, change the charge. Change the neutron. Oh, you're jumping ahead. That comes after we change this. We add a neutron, or maybe we take away a neutron. What are we changing? Huh? The mass. Perfect. Change the mass and you get a isotope. Okay, an isotope is what we call an atom that has gained or lost neutrons. It's not an ion. Electrons aren't changing. It's not a different element. Protons aren't changing. It is an isotope of the original element because we changed the mass by removing or adding neutrons. Now, not all elements like being isotopes. We have stable isotopes, aka those that don't mind, and so they remain in that state and it doesn't matter, like carbon to an extent, okay? Or you have unstable isotopes. And those unstable ones are going to decay. They have entered a state of instability, and they are going to decay until they reach a new stable condition. These unstable isotopes, going through decay, put off what we call radiation. Radiation are those particles, protons, neutrons, and electrons being blasted off of this unstable isotope until enough of them are lost that it has become a new element which is stable. Common example, uranium. Uranium-235. Remember we talked about radiometric dating last time, right? Uranium-235 will decay until it reaches lead-207. Remember that? Took like more than 700 million years for one half-life to go through that. But when it does, it becomes a new stable element, lead-207. Now, humans being humans, we played around with this natural process, and we figured out that we could use this in a couple of different ways. What are some ways that we can use unstable isotopes? Power generation, perfect. Nuclear reactors. How many of you know what a nuclear reactor is? Kinda? Okay, not so sure. Start over here. Tell me something about a nuclear reactor.
It produces heat or steam, nuclear reaction, something like that.
It does. Thank you, Alan.
A fission reaction is produced which heats water and spins I think it's a turbine.
Okay. So you used the word there, fission. What does fission mean? Huh? When you combine two nuclear elements, it's called fusion. No? Why are we yelling numbers? 42. See, I can do it too. What does fission do? If fusion binds new atoms together, then fission must be separating. Now, fission is ripping them apart from each other. Okay? So fission rips them apart. Fusion pulls them back together. Both of these happen in the sun constantly, simultaneously, by the way. Okay? But we are only capable of one, fission. Technically, we've reached a technological state, I believe, where we could actually make fusion. But here's the problem. Fusion takes a lot more energy to get started. Once you get that process started, it can be sustaining. But it takes so much energy to start fusion that we cannot, with the current infrastructure we have, do it. I think I read it somewhere that said that if we could take 100 nuclear reactors that we can make right now and pool all their energy, we could start a fusion reactor. Now, that might actually be worth it and something that people will explore in the future. But right now, people are leery enough about nuclear power that constructing a complex with 100 different nuclear reactors on it is not happening anytime soon. Okay? So while we are at the technological place where we could probably do it, we are not yet at the societal place where we can do that yet. Although I have heard one fascinating concept of, well, okay, if you don't want to do it here, why don't we just do it on the moon? And I'm like, I like that one, right? Yeah, let's make 100 nuclear reactors on the moon. If something bad happens, sure, it's harder to fix, but it also doesn't put anyone in danger, right? So, anyways, that was a tangent. Let's talk about fission again. Fission. Ripping things apart. In a nuclear reactor, what you do is you take rods of this unstable isotope, like uranium-235. Let's say that I have a rod of uranium-235. I'm holding it in my hand. Very unwise. Okay? It's putting off a lot of radiation right now. I'm probably going to die, and very soon. But what would happen if, say, I took that rod and I put it next to another rod doing the exact same thing? I now have twice as much radiation flowing through my body, slowly disintegrating me cell by cell. But the closer I put them together, the hotter things get. Why? Because both rods of uranium are blasting radiation off in all directions, but when I make them approach each other, all that radiation is interacting with itself, with each other, zinging off in all sorts of different directions, generating tons of heat. Not literal tons, but you know what I'm saying. Tons is an expression of a lot. Okay? Lots and lots of heat. The closer I put these rods together, the hotter things get because that radiation is slamming into other radioactive particles, generating heat as a consequence. Now, this can lead very quickly to what we refer to as a meltdown. Everything around this process gets so hot, it literally melts. Anytime you hear of a nuclear meltdown, it's because that process ran out of control and the facilities built around that reactor to contain the radiation fail. So how do we keep that from happening? Coolant. Normally water. Okay? Well, actually, it used to be water. It's not water anymore. It's often some form of salt. Okay? Liquid salt that they put around these things. Okay? So you have your nuclear reactor or your nuclear rods, okay? And it heats up some medium, some liquid, usually very dense, highly energy absorbent liquid, okay? And then there are pipes of water around that chamber. And water is put through those pipes and instantly gets flash vaporized to steam by the intense heat, okay? So this intense heat vaporizes that water. That steam blasts down the pipe and spins a turbine. Attached to that turbine is a magnet. And attached to a turbine that spins in the opposite direction on the other side is another magnet. And so try doing this, by the way. It's not that, it's not that hard. It's not that easy, is it? Right? But these magnets that are spinning in opposite directions are generating an electromagnetic field between them. Okay? And that electromagnetic field is what we capture and pipe through all of our electrical wires and all of that. So that's how a nuclear reactor generates electricity. Very, actually, basic when you think about it. The same thing we've been doing with coal mines for a long time, okay? Or with the coal power plants, where the heat from the fire of burning the coal would generate steam, and that would turn a turbine, so on and so forth. We just do that with nuclear now, okay? Or we can. There's not that many. So that's one thing that we've learned how to do with isotopes. What's another thing? There's two more, one of which we talked about last week. Radiometric. Dating, thank you. What's the last thing that I guarantee you know about that we figured out we could do with isotopes? Yes, we figured out how to make things go boom. All that energy that radiation releases from uranium-235 over 700 plus million years. What if I figured out how to split that atom and release it all at once? Lights the atmosphere on fire. Sends out lots of radiation. Okay. Usually what you'll do to make a nuclear weapon is you'll have a quantity of unstable isotope. Depending on the isotope, you'll have either a dirty bomb or a clean bomb. I'll explain the difference between those two in a minute. And then you'll arrange some sort of explosive device. Okay. So the way that you can most efficiently split an atom is you make a high energy, very precise release of energy in that unstable isotope. And by adding so much more energy to that isotope, you cause it to rip itself apart and start that fission eruption. And then there's a chain reaction of fission throughout the rest of the unstable isotope mass that you have there. So you might have half a kilogram, or not half a kilogram, excuse me, just half a gram even just of unstable isotope like uranium-235, just the very smallest amount. And then you have a package of high explosive like C4. And then you put it into a bomb such that when that bomb impacts something, when it drops to the ground, or maybe when a timer goes off, there is some percussion cap on that C4, blows up the C4. All that C4 energy, the explosion from that C4, it causes one or a few maybe of the isotopes of that uranium to rupture apart in a fission reaction, which adds enough energy to cause the rest of those unstable isotopes to also rupture apart and become fissile, okay, to destroy themselves, releasing all of that held energy all at once, and that's what makes a nuclear weapon. A dirty bomb is when you have so much unstable isotope mass in there that when the bomb explodes, it spreads radioactive particles everywhere. That's why we call it a dirty bomb. It leaves a lot of fallout. A clean nuclear bomb, it is possible to make those. using materials that don't generate a lot of radiation. It might be unsafe for a few weeks, but then whoever dropped the bomb could go for a walk over there and be totally fine. It's the sort of weapon you use if you want to conquer and take something over. A dirty bomb is what you use if you don't care about that area. That's more of a terror type of weapon. Okay? Yeah, that's how those work. Yeah.
And how is a hydro bomb?
Hydrogen bomb. Yeah, a hydrogen bomb is far, far more powerful than your standard nuclear weapon that uses an unstable isotope. Why? Well, if that's how much energy you release from destroying an unstable, already falling apart, decaying isotope, how much more energy is there bound up in an element that is not already in a state of decay? So by splitting a hydrogen atom, the most basic, simple atom on our periodic table, by splitting that, you release 100 times more energy than you would in a standard nuclear weapon. So hydrogen weapons are technically illegal because the testing of those things has proven to be so destructive that everyone is terrified of what would happen if they were used. It would take probably 100 standard nuclear weapon, probably 25 megaton nuclear weapons to reduce the worldwide civilization to a state of pre-industrialism. Strategically placed in our biggest communities and our biggest cities, where the biggest military and technology infrastructure are, you could probably reduce humanity on this planet back to the Stone Age, or at least pre-industrial civilization with 100 standard nukes.
Is that what Oppenheimer is, the hydrogen bomb?
No, his was the standard nuclear weapon. Yeah. Hydrogen bomb is far, far worse than that. A hydrogen bomb, it would only maybe take 10 hydrogen bombs around the planet. You could annihilate most of the infrastructure, vital government and military logistical infrastructure of the United States by putting one hydrogen bomb in the right location on the East Coast. You take out multiple major cities all at once. You can blow it up in one, but then the shock wave, the fire wave, the overall destruction, and the earthquake that accompanies that would effectively eliminate the other cities enough that it wouldn't matter whether the bomb was in there or not. The Tsar Bomba was the largest nuclear weapon ever used. It was a hydrogen weapon. It was blown up on this island up here above Russia. That banana-shaped island right there, they blew it up right there. And it shattered windows across all of Europe and was felt by earthquake sensors across the entire planet. It was no secret. Everyone knew what happened because it showed up on every monitoring device on the planet. I don't know if anyone has actually proven it because this was long enough ago that we weren't really monitoring this particular thing. But it's believed that it actually very, very ever so slightly changed Earth's rotation. An explosion so powerful that it shook the planet enough to barely, ever so slightly change the very nature of our planet's orbit around the sun. Now, you set off enough weapons like that in just the right places across the continents where the most people live, that have the most infrastructure, the most technology, and that's it, right? So that's how powerful these things are. Definitely not things to be trifled with, which is why every spy thriller ever written for the last 40 years has been, they've got nukes, right? It's terrifying, really, when you think about it. For those of you that remember, were your parents alive during the Cold War? When were your parents born? 19. Okay, so at least some of y'all's parents remember the Cold War. Okay? It was a terrifying time because there were things like that in the wind, and the nations were still trying to come together and agree on what can be used, what can't be used, what circumstances, all of that.
I remember watching the wall come down. It was like on every channel on
Yeah.
TV. When I was a little kid watching the
Yeah.
The wall come down. So yeah, I remember.
Yeah.
I'm that old.
Good old Gorbachev. Yeah. The world is still a terrifying place, just less overtly, if that makes any sense. Those weapons are still out there, and they're still part of our society. I say nuke, and everyone knows what I mean. But it's less visceral for our generation here than it was for our parents. There were still active tests going on, right? And it came close. Stanislav Petrov, you ever heard of him? Do you know who I'm talking about? Stanislav Petrov was the commander of a Russian submarine. And he was under standing orders during the Cold War that if he observed nuclear launches from America, he was to launch his nuclear weapons at America, and he had specific targets to hit. One day, an alarm sounded on the sub, and it said America had launched missiles. It didn't say where they were going, just that America had launched them. And his standing orders were, if you observe that America launches, you launch at them. But he had not received any orders. He had not heard anything from any of the submarines. He had not heard anything. Something didn't feel right. Every other officer on that bridge was yelling at him to follow his orders, but he refused to turn the key. And it turned out they ran a diagnostic, and their computer just fritzed out. There had never been any launches. Clearly, we're all still here. We owe the fact that we didn't devolve into a nuclear war to one man, Stanislav Petrov, who followed his gut instead of his orders. He thought to himself, we haven't heard of anything that would prompt America to launch against us. Why would they launch? Something's not right. If he had launched, we would have gone into nuclear war that day, because he would have launched and then America really would have launched. That's how close we came. So, not a joke. All right. Any questions or comments before we move on? All righty. So let's talk about minerals then, now that we've had our memories refreshed on atoms and elements. A mineral is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. That sounds familiar, right? Hopefully you all still have that down. If not memorized, at least written down. And if you don't have it written down, please do so. Again, very important. Word for word. That is the definition we are using in my class. If you try Googling the definition of a mineral, you'll get a variation on that theme. But I encourage you to use this variation within the bounds of my classroom. Okay? A rock is a whole bunch of minerals that are all gathered together in one unit. Thus, a rock is made out of minerals, but a mineral is not a rock. You following me on that logic? Do you remember the example I gave early on in 1403 to help you remember the difference between a mineral and a rock? Yeah, ingredients for what? What do I always use as an example? It's a cookie! Yeah, the ingredients for a cookie. Ah, y'all know me so well. Yeah, so where the rock is my chocolate chip cookie, each ingredient is the mineral. We've got the feldspar and the amphibole and the biotite and the quartz, like the flour and the chocolate chips and the butter and the salt and the cookie. And granite is my cookie. Okay? Think of it like that. Each mineral is something we can tell apart from the others based upon their properties. And properties include things like their optical properties, aka how they interact with light. Does it pass through them and does it reflect off of them? Their crystal shape. Their strength or hardness, okay? That's the measure of their resistance against another substance. You can use another mineral or another substance of a known quantity like steel or glass, okay? Then there's density, taste, texture, smell, magnetism, etc. Now, this last one, effervescence, it's right here, okay? Effervescence, I need to put just let you all know how to spell it. I need to make sure that you all remember how to spell that. I can't tell you the number of assignments I've gotten that talked about a mineral's evanescence. It's not a group, okay? It's not a musical group. Although I do love their music, by the way. Yes, they have great music. I went to a rock orchestra concert last week on Wednesday, and they played some Evanescence, and it was like, ah, yes, okay? But it's not this. It's effervescence, okay? Alrighty. That's effervescence. The fizzing that you get when you put hydrochloric acid on certain minerals. You learned about a couple that have this effect, okay? That have this reaction. So just going over these properties a little bit more. Your luster, that's the appearance of how light reflects off of your surface. It can be metallic, it can be glassy, it can be pearly, it can be resinous, like dry tree sap is resinous, right? Then there's the light transmission. Is it opaque, transparent, or translucent? Someone remind me what the difference between transparent and translucent are.
You can see through something that's transparent. Translucent is just kind of like a blurry.
Right, yeah. So with translucent, you get light that can pass through it. In transparent, light and an image can go through it, right? So imagine if it were foggy. Right now in this room, no fog. The air is transparent. I can see each of you through it. But if I filled this room, if I put a fog machine in here and I filled it with a cloud, I'd be able to turn on my flashlight and you'd see it, but you probably wouldn't be able to see me. That would be translucent. Okay? And then there's the color. And what makes the individual colors? It's the impurities or the inclusions in those minerals much of the time. Whatever is in that mineral dictates its color. Now, that's why color is not a primary identifying property, is because I can have quartz that is purple, quartz that is black, quartz that is white, and quartz that is brown or yellow. All of them are quartz. They are all the same mineral, SiO2. That's their chemical composition. However, if I have a little iron in there, it'll be SiO2 parentheses Fe, right? Because I also have some iron in there giving it that color. Or SiO2 parentheses U. There's a little bit of uranium in here, right? There might be a little bit of calcium in there. Whatever the case may be, that's what gives it the color. That's why we don't use color as a primary identifier, because this color is the same thing that you could find in fluorite, is the same thing you could find in lepidolite, is the same thing you could find in corundum. At best, color is a tiebreaker. And it is the one that everyone is tempted to use first, until you know and understand geology, like you all do now, right? Okay, streak. When I take my mineral and I scratch it on a streak plate, aka one made from unglazed porcelain, white or black, it leaves some color behind. That color is an identifier, a property we can help use to identify these minerals. Now, under what circumstance would it not leave a streak behind? Yes, if the mineral is harder than my streak plate, it will not leave a streak behind. For those of you getting PTSD about this, I'm not going to make you identify any minerals today, okay? This is review, because this is relevant to some things that come later. You are getting a lab today, but it's not like what you got before. All right, crystal shapes. These include things such as, these are dodecahedrons, 8-sided shapes. Sorry, those are octahedrons. Dodecahedrons are 12-sided shapes, like right here. Cubes, these 6-sided shapes, these occur naturally. Okay, many minerals form geometric shapes, and that's based upon their internal atomic structure. Okay, what shapes do their chemical bonds make? Those are going to be manifest in the external geometric shape that they form. Then your tenacity, your resistance to breaking, essentially. So when I hit a mineral, does it bend? Does it reshape itself like gold would? Does it shatter like glass would? Things like that. Your hardness, measured of mineral resistance, we already talked about this. You remember you scratched it on glass to figure out what it was you were looking at. There's the cleavage, shudder, right? Mineral cleavage is how a mineral breaks based upon its internal atomic structure, the planes of weakness that are present there. Okay? Not all bonds are as strong as other bonds. And so when I put pressure on a mineral, it will break along the weaker bonds before it breaks along the stronger bonds, and thus we will see cleavage manifest in the mineral while it's breaking. If there is no cleavage, then it's got fracture. Fracture being whatever random way that that mineral tends to break. In the case of quartz, it makes a conchoidal fracture like that. Then there's the density. We didn't really worry too much about the density in this class. There is a world where part of your lab is to figure out the density of a mineral, but that takes a little bit longer and it's not strictly necessary, so I eliminated that from the curriculum. Then there's all those other properties we talked about, your taste, texture, smell, all yada, yada, yada. Please, again, if you do feel the prompting to go and lick one of those minerals, don't lick 18 or 37. Just reminding you all. Okay, there are lots and lots of minerals, more than 4,000 different varieties, and growing. Some of them are actually pretty rare. Okay, places you can present in only a few places on Earth. Why did that happen? Why would there be a mineral that is only present in one possible location? Well, this is because of a unique set of circumstances that occurred in that one location. Perhaps it was tectonic. Perhaps there was a unique chemical recipe for a magma in a magma chamber. Something that it's pure coincidence that it could have happened. And now we find the remnants of that, and that's why it's the only place on Earth, right? There are a few gemstones you can only find in a few places on Earth because of unique set of circumstances that cause them to be formed there, right? So most of those minerals that you are going to encounter in your everyday life are the ones that we learned about in 1403. Okay, the 50 minerals that I showed you in 1403 are going to be 99.9% of all the minerals you see in your life. Our non-silicate minerals are often associated with sedimentary rock deposits. Okay, so you've got your silicates, which formed from igneous processes, right? Why do we call them silicates? They're based around that silicon tetrahedron structure. Our non-silicates are the ones that are not based around that. It's about 8% or so of all the rock in the crust are non-silicates. And like I said, they are most commonly associated with sedimentary rock cycles or within sedimentary rocks themselves. Bless you. We differentiate them all from each other based upon the ion that they have in common with each other. So for our sulfides, we've got galena, sphalerite, pyrite, so on and so forth, because those are all sulfide. Okay? They all have this 2 negative sulfur ion in common. Native elements. What is a native element? Well, that's just an element that's totally on its own. We find gold with gold. We find silver with silver. We find carbon with carbon, so on and so forth. Gold is just gold. Diamond is just carbon. Graphite is just carbon. So when we find groups of, or I should say, minerals that are made entirely out of just one element, we call that native elements. Okay. All right, before we move on to igneous rocks, any questions about minerals? Cool. You're all still experts on it. I love it. Okay. Igneous rocks are made from crystallized, solidified magmas and lavas. Now, if it's formed from a lava, aka at the surface, we will call it an extrusive igneous rock. This is a description of its cooling environment, nothing else. Nothing about composition or anything is tied up in this word. Okay? Extrusive only means it cooled at or near the surface. Intrusive means it cooled where?
Above ground. Or wait, intrusive?
Intrusive,
In
yes.
the ground?
In the ground. Usually fairly deep underground, okay? And how do we tell the difference between intrusive and extrusive igneous rocks?
The intrusive are coarse grained.
There you go. Larger crystal sizes in your intrusive igneous rocks. Extrusive igneous rocks cooled faster and therefore didn't have time to grow large minerals. Whereas the intrusive igneous rocks cooled slower and there was more time for those minerals to grow. Okay? Oh man, one of my contact lenses just went really fuzzy for no reason. All right. Now, let's talk about composition. The composition of an igneous rock is determined by the composition of the lava or magma that made it. The composition of the lava or magma is based upon a few factors. You remember learning about Bowen's reaction series? Yeah. Bowen's reaction series is the sequence that of what minerals form as a magma chamber is cooling off over time. As more time passes and more minerals are formed in my magma, those minerals take certain elements out of the magma and change the overall composition, which in turn determines what minerals or rocks come from that magma. So let's start off with a discussion of felsic. Felsic is high in silica content and low in iron and magnesium content. This will make rocks like granite. Mafic, high in iron and magnesium content, low in silica content. It'll make rocks like basalt. Between those two, we've got intermediate, otherwise known as andesitic. Why? Well, because it will make a mineral or a rock called andesite. Or diorite as well. You may recall diorite a little better. That zebra rock, right? Where it seemed equal parts white and black, right? That's intermediate, somewhere between felsic and mafic. Then you've got ultramafic, meaning from deep, deep underground, mantle rock, basically. And that's going to be your periddotites, like this guy right here, where it's pretty much just olivine and a little pyroxene, the minerals that occur in the mantle. We good on igneous rocks? Great. Moving on to sedimentary rocks. We classify sedimentary rocks as clastic or non-clastic. Organic go under the non-clastic category, but in this class there's a little bit more significance to them than there has been in 1403. Because we get so many fossils from organic, non-clastic sedimentary rocks, we're going to be considering them a little bit differently than we did in 1403. Okay? So your clastic sedimentary rocks are those made from the physically weathered components of other previously existing rocks. So that granite I had earlier got weathered and eroded and broken down into small pieces. Those small pieces got compressed and turned into a classic sedimentary rock. What if the feldspar in that granite was instead chemically weathered, reduced to things like calcium and potassium and clay and a few other ions, and those ions went out into the ocean and then reprecipitated as a new mineral which fell to the bottom of the ocean and then got turned into limestone. That would make a non-clastic sedimentary rock. A non-clastic sedimentary rock are those made from the chemically weathered remains of other rocks. And your organic are obviously those which are tied into the living process of living things, okay, of the life process of living things. So things like fossiliferous limestone. Why do we call it fossiliferous limestone? It's made out of fossils. Those fossils were once part of something alive. That rock would not exist without those things having lived. Therefore, we consider that a form of organic sedimentary rock. Then you've got coal, right? Coal being the remains of plants that were compressed and heated and became a rock, more or less. We call that an organic sedimentary rock. Let's talk about clastics here for a second. We tell clastic sedimentary rocks from each other based upon a few characteristics like their grain size, also known as particle size, okay? Grain size, how large they are, usually in millimeters, okay? And we have a scale for that. 2 millimeters and larger being gravels, 2 millimeters to yada yada being sand, so on and so forth. You've got the scale up here. We don't need to go into all that. I'm just refreshing your memories. Grain size or grain rounding, okay? How rounded my grains are versus how angular they are determines, or not determines, but tells me a little bit about how far that sediment traveled, how far it was, how much it was weathered, and how far it may have been eroded away before becoming a part of that rock. Then there's the sorting. How many of these grain sizes are like the other grain sizes? Are about the same size, in other words, okay? All of these tell a story about the background of this rock. By telling me a little bit about the things that make that rock, I get a little bit more about the background of that rock. Okay, our chemical sedimentary rocks. I already told you about the inorganic ones. Things like micrite limestone, travertine, chert, like what makes geodes and agates. All of these form as a result of chemically weathered minerals, and the chemical remains of them going through the water system ultimately cause those chemical remains to reprecipitate. Sometimes it's because water evaporates away. Sometimes it's because the concentration of dissolved minerals in the water gets so high that it starts to grow minerals wherever it can, like what happens with agates and geodes. Okay? These are, this is the same thing in micrite limestone, by the way, out in the ocean. These are your inorganic, non-classic sedimentary rocks. Now, let's talk about the organic ones. Coal being probably the one that you're most familiar with. Plants and algae sometimes. Things like moss. All of that can be incorporated into this process where you have some anoxic environment. Do you know what anoxic means? I'll give you a hint. If oxic means presence of oxygen, anoxic must mean, yeah, no to very little oxygen. An anoxic environment, somewhere like a swamp, where you have water that is not renewed very often, okay? And so, anytime plants fall into that water, they fall to the bottom, bacteria does its thing, starts to chew away and eat up that organic mass. It's going to suck up the oxygen in the water, which means that eventually you're going to reach an anoxic environment in that water, which means that decay cannot continue. And as more plants fall into this anoxic environment, they don't decay away, they don't rot, they just get piled deeper and deeper and deeper and shoved deeper underground as new stuff is piled on top of them. Ultimately, you are going to end up with a compacted plant matter, and that's your first step for making coal. And the deeper it gets shoved underground, the hotter it gets, the more pressurized it gets, and the better the quality of the coal becomes. Okay? The more dense, the more compact. It's a lot of potential energy all tied up in one substance. It's a hydrocarbon fuel, organic fuel. Now we can use all the information, all of the stuff that we know about igneous rocks and about sedimentary rocks to make very clear interpretations about past environments on our planet. We can piece together the history of our planet very nicely with what we know from these two types of rocks. Next up is metamorphic rocks. Metamorphic rocks are a little bit trickier because they are produced through chemical alteration, which means that after a rock is metamorphosed, it's very difficult to know what environment could have made the rock that was there before. That rock isn't there anymore. I am now working with a metamorphic rock. It kind of resets the clock, so to speak, on that rock. Okay? Where before I could tell how old an igneous rock was and where it may have come from by its chemical signature and stuff, after metamorphosis, it's a totally different rock. All that information is gone. But the circumstances that make that metamorphic rock are interesting in and of themselves, usually tied to tectonics, one way or another. And so I can figure out more about that tectonic event by studying the metamorphic rocks themselves. Metamorphism is caused by two factors, heat and pressure. Heat comes from a couple of different sources. The geothermal gradient, things getting buried deeper underground, basically. Also, plate tectonics can cause friction, also makes some pressure, right? But the friction of the plate tectonics can make enough heat for metamorphism. Rising magma chambers can bring heat with them and cause metamorphism around them. These are all sources of that heat. And this heat will provide the energy and even sometimes some new ingredients for our cookie, right? Such that we can end up with brand new metamorphic rocks as a result of the metamorphism process. Here's that diagram showing the different heat sources. Now, what about pressure? There were two types of pressure we learned about in 1403 in metamorphism. What were they? If you don't remember the names, just describe them to me.
When they're getting shut down.
Keep going.
Push down, and then, like, would it make that niece with the layers? No?
I mean, yes, but you're like combining two different types there. Anyone want to help her out here? Describing, no? Don't have anything? All right. How about I say the name and then you tell me what kind of pressure it is. Confining pressure. Tell me what it is.
Something in a small space getting really condensed.
I mean, this space is relative, right? It could be a large area, it could be a small area. But confining pressure, that's a force. What's causing it? Or to tell me, I guess, what it is. Remember I gave you the example of imagine you're at the bottom of a 12-foot pool. Feel that pressure from around you in every direction. Confining pressure is equal pressure on a point from all directions. The size of the area is irrelevant. I could be talking about a mile square area, or I could be talking about the end of a pin. Confining pressure, though, that's a force that I can measure on that area regardless of the size. Okay? So confining pressure is equal pressure from all directions. Now that I've jogged your memory a little bit, someone tell me about differential stress.
Pressure applied unevenly.
Uneven pressure. Yes. That's the logical conclusion. Just let's keep going. Unequal pressure, how so, and what does that do?
It causes foliation in the rock.
Okay, so it's going to cause things like foliation. Differential stress is when I have unequal stress from two different directions. So instead of having, on the end of my finger, instead of having 360 degrees all around me in every direction of pressure on the point of my finger, I have pressure coming from two different directions, okay, causing unequal stress. That's differential stress. And it does do things like cause folding in layers of rock. It causes foliation of minerals. Now remind me what foliation is. Folding happens in rock layers. Foliation, caused by the same force, happens to individual minerals. I'm asking what foliation is. That's what we just talked about over here. Yeah.
Isn't it the mattress thingies that you use?
That was folding. Yeah, I showed you the layers of foam to show you folding. Foliation is a similar thing, but instead of happening to one linear layer, we're talking about individual minerals. The layers folded in response to that stress. And in what direction do they fold? Huh? Yeah, but oriented to the stress how? Perpendicular to the stress, yes. So layers will fold perpendicular to the stress, aka up and down, if my pressure is coming from the left and right in this example, right? What will individual minerals do? They'll foliate. But what is that? Foliation is when minerals will reorient themselves perpendicular to that direction of stress. Okay? Individual minerals aren't going to fold, but they will change their orientation. Some of them recrystallize, some of them get flattened, and some of them just move. Okay? So you could have one that just reorients itself. You could have a big round one that gets squished perpendicular to stress. Or you could have like another one that just like kind of reshapes itself to go that direction. Those are the three ways that you end up with foliation in metamorphic rocks. Okay, any questions about minerals, sedimentary rocks, igneous rocks, metamorphic rocks, or any of those processes? Do your memories feel sufficiently renewed on the matter? Okay, well then one more quick note. Mineral resources. We started off with a conversation about mineral resources, about rare earth metals in China. Mineral resources are extremely important. Without them, our civilization simply ceases to work. Okay? This is a picture from a salt mine, by the way. How many of you knew that we often will mine our salt? You know that pink Himalayan salt that you see in the grinders, right? That comes out of a mine. The fancy salt, yeah.
They sometimes found in water.
In water?
Yeah, I found it.
I mean, yeah, there's a little bit of it in the ocean. Yeah.
I've seen some like villages that get salt water from old.
Yeah, you can. You can get ocean salt. Sea salt is used for a lot of stuff, but the fancy salt, the nice culinary salt, that comes from a mine. Okay, so there are mines of salt in everywhere from Louisiana to Turkey. Okay, but that is just one example of the many resources that we need to constantly be replenishing in our society to survive. By the way, oil. We can think of that as a mineral resource if you like. We extract it from the rock. Okay? How many of you learned in school that oil came from dinosaurs? Sorry, it didn't. Yeah. I know, heartbreaker. It's a heartbreaker to learn. No, there were not nearly enough dinosaurs to make oil. However, for every one dinosaur, there was 1 million trees, right? Trees, algae, other underwater plants, those the little tiny little animals like planktons and zooplanktons in the ocean, those are what make the majority of our oil mass on our planet. Okay, any questions about today's lecture at all? Well then, I will tell you about your first lab, and then we can get to work on it. Oh, hello, that's me. All right. Your lab 1 is just going over sedimentary rocks and structures. This is all stuff from 1403, just reminding you what the significance of sedimentary rocks are. They cover most of the surface of our planet. 70% of all rock on the surface exposed to the atmosphere is sedimentary rock, or the ocean, I suppose we could say, right? Is sedimentary. Even though most of the crust is igneous and metamorphic, most of the exposed rock is sedimentary, which makes it most relevant to us because guess what? We live on the surface, right? So, very important for us to study and to learn about. We'll go with that. Okay, so just to remind you of a few of the more common examples of sedimentary rock, you got things like shale, made from very, very small clay and silt-sized particles that are deposited in very thin layers. We call them laminae. Okay, laminated rock. That's what those tiny little thin layers are. This forms in very low energy environments, deep oceans, lakes. If a river floods and it leaves a small layer of sediment, it'll leave that sediment can sometimes go on to become shale. Okay, sandstone, larger particles. Okay, from 1/16 to 2 millimeters in size. These are most commonly made from sand particles. Wow, not sand. From quartz particles. Sand is most commonly quartz, although it can be at times made from a few other minerals like olivines in some places, or feldspar, which if it's mostly a feldspar, or if there's a high quantity of feldspar, then I would refer to that sandstone as an arkose, right? We've got different names for these different kinds of sandstone depending on their ingredients and so on and so forth. But it's mostly quartz. Then you've got the next size up, you've got your conglomerates. Conglomerates are made from anything larger than a grain of sand, right? If your grains are angular, then it's going to be a type of conglomerate called a breccia, right? Like this. Angular fragments in there, breccia. Rounded fragments, we just call it a conglomerate. Our chemical sedimentary rocks, limestones. There are different types of limestones. Your inorganic micrites, right, where there are no fossils. It's just tiny little crystals of calcite that precipitated in the ocean, fell to the bottom, and then got compacted. Then you've got your biochemical ones, your fossil limestones. Chalk. Chalk is a type of limestone made from tiny little microfossils of things like planktons and coccolithophores and radiolarians and foraminiferans and all these tiny little wee beasties that we're going to be learning about later on in the semester. Okay? Dolostone is a variety, I suppose you could say, where all of the limestone, in the limestone, all the calcite has been turned to dolomite. And so where you've got calcite and dolomite as minerals, you have limestone and dolostone as the rocks made out of those individual minerals. It looks just like limestone, but it won't react to acid like limestone will. You'll have to scratch it and powder it first. Then you've got cherts, and cherts are made from microcrystalline quartz. I've got tons of chert up here. This agate is made out of chert. That rock is probably chert. Those trees have been replaced by chert in the fossilization process. So there's chert everywhere. Microcrystalline quartz, that was the silicon ions were made as a result of the chemical dissolution of other silicate minerals. And then your evaporates, things like salt and gypsum. As water evaporates away, it leaves behind whatever minerals were dissolved in it in the first place. We already talked about coal. We don't need to go over that again. Okay, so the process by which the sediment becomes a sedimentary rock is called diagenesis. Diagenesis is any change that occurs to a sediment after deposition, but before metamorphism. Okay, so we have not started turning this into a metamorphic rock yet, but there is some heat and some pressure required for diagenesis. So there's that squeezing, that compaction, and some cementation. As you are squeezing water and air out from between these particles and crushing them closer together, there's going to be some small mineral crystals that grow on the outside of those minerals. We call that a cement, and it holds your grains together. The better the cementation is, the harder your rock is, the harder it is to break it apart. There are sandstones that are so easy to break apart, I can crumble them in my hand. And there are other ones that are so tightly bound together by silica, by microcrystalline silica, that I can use them to cut glass. Right? It just depends on what's in there. Okay, so for the structures, a structure is a relic of whatever was going on in the environment at the time that the sediment was deposited, right? So if I've got ripples in there, I know I'm probably looking at some shallow water, shallow running water. If I've got mud cracks, I know I'm probably looking at some water body that evaporated away, right? So we can make conclusions of the environment based on the structures that are preserved there. So for example, these are some ripples. These are two different types of ripples, asymmetrical and symmetrical. In an asymmetrical ripple, you will have one direction of flow. In an asymmetrical ripple, you're going to see that you have one very low angle slope and a very steep angle slope over here. Does this remind you of anything that we learned about? Kind of like waves? Not so much. What about dunes? Yeah. Yeah, it looks a lot like dunes, huh? It's the same thing, where wind or water is blowing in a certain direction, right? In just one direction, it's going to make our sediment pile up in that direction, as if it's moving that way. So you get a low angle from the direction that the fluid is coming from, and a steep angle in the direction it's going, like a dune would. This is an asymmetrical ripple. What about an symmetrical ripple? What does that mean? Symmetrical now.
Isn't that one more like waves?
Right. So we have two directions. So we've got fluid going that way and then that way and then that way and that way. And so the two halves of our ripple are approximately symmetrical with each other. Name an environment where we have water going back and forth. A beach. Yes. So you'll see symmetrical ripples at a place like a beach. Tell me an environment where we would see asymmetrical ripples. One direction of flow. Rivers. Good. Okay, see, you're already making interpretations based on sedimentary structures. The system works. Okay. Trace fossils. These are evidence of life without actually being part of that life itself, like a footprint. If I left a footprint in the sand, would anyone, any of you, go up and be like, oh, it's a piece of Professor Hart. He just left it there. I should return it, right? No, you wouldn't say that because it's not a piece of me, but it is evidence I was there. That's what a trace fossil is, okay? These are dinosaur footprints. Really cool. There's actually some of these not that far from here. I wish that I could get the approval and funding to take you all on a little field trip. I would take you to some dinosaur footprints. They're only about an hour away from here. But unfortunately, that's not in the books right now. Yeah. There is a rest stop out, you go to Iran and then you take a hard right, and I forget what that town out there is called. There's a rest stop out there where they actually have a steel cage built around dinosaur footprints in the rock. Yeah, it's just out there behind the rest stop. There's actually a place not far from there as well where we could go hunt for ammonite fossils. These are all goals of things that I want to get going, but I just have not, A, had the time to fight for it enough. And because I haven't had the time to fight for it enough, B, people haven't approved it. I hope that I can do that maybe this year. Okay. Real fossils, like these are pictures that I've taken of ones that I've found, are always in sedimentary rock. You can't find fossils in any other kind of rock. Fossils are great because they tell us, yes, these things did live. These are pieces of them. Okay. How long ago did they live? Well, I can figure that out. What was their life cycle like? I can figure that out. What did they eat? Where did they poop? Where did they sleep? Right? How tall were they? Right? What were their childhoods like? How long were their life cycles? These are all things I can figure out by studying fossils. These are types of fossils called stromatolites. Have you ever heard of them before? Oh, you're going to hear about them a lot in this class. Stromatolites are the oldest type of life that we know about on our planet. Stromatolites, there are fossils 3.4 billion years old. These are mats of algae, okay? So simple colonial bacteria that lived in shallow water, and when the tide would go out, they'd be exposed a little to the air, maybe just in even shallow water, and then the tide would come back in and deposit a small layer of sediment on top of them. And they would have to grow up to be exposed to the sun again to keep photosynthesizing. And then the tide would go out and come back in and bring another layer of sediment, and they'd have to grow up above it a little bit more. So we get this layering effect of algae, sediment, algae, sediment, algae, sediment, building up until eventually you get these mounds. And these stromatolites take on these sort of weird mushroom sort of moundy shapes. These are real stromatolites that are still alive in Australia. This is Shark Cove, Australia, I believe it's called. Stromatolites have been on this planet for more than almost 3.5 billion years. And they're still here. They stuck through it. We'll talk a lot about their history in the fossil record later on. But yeah, do not confuse these with these. This is often something that gets people confused. These are not stromatolites, even though some of them might share the same shape. These are called iron concretions. In an iron concretion, you have iron sulfides or iron hydroxides that are in your water. And they collect around some object. Sometimes it's a fossil, sometimes it's a rock, sometimes it's a random void in my sedimentary rock. But you get these iron that collects around something and makes an iron concretion. Okay? Again, you can see how easy it would be to confuse those with each other. Just bear that in mind. Made out of iron, and that's a fossil. Okay? So, let's pull up your exercise. Can I do that without showing you the answers? I think I can. Call me the little engine that could. Okay, yes, this is the exercise that you're going to see on Blackboard. I give you some characteristics and I ask you to tell me what it is. That's it. What sedimentary rock is this? Hint, it's detrital, aka clastic. It has a grain size of 1/16 to 2 millimeters. And I ask, is it well sorted? Right? So you're just answering these basic questions for each of these. And then I ask you about a few structures. And then the only part of this that is really kind of tricky, there's a couple questions here. The only part of this that is really kind of tricky is a table. And it looks a little different on Blackboard than this. You'll see what I mean when you get there. But this is essentially what it comes down to, is matching the structure to the appropriate environment that it could be found in. Okay? Any questions about your lab? No? Well, I've been talking long enough then, so I'm just going to end this, and we'll get started on the lab.